Okay, we are live now. Feel free to start when you are ready.
Sure. So, hello everyone. My name is Kairav Thakkar. I am a blockchain and AI developer, and today I'm going to present the concept of distributed key generation. I would like to extend my gratitude to the Dora Dojo and the DoraHacks team for allowing to present the concept and also providing the required support and guidance to learn and deep dive into this concept. So, yeah. So, let's just understand what we are going to get out of this workshop. Uh, First, we are going to understand what distributed key generation is. So I'm just going to introduce the topic, make it uh, as easy as possible to understand. Then we are going to go and delve into the core concepts around this topic. We're also going to look into the practical aspects of this, how distributed key generation is being operated practically in the real world, how it can be operated in the future. We're going to look at the applications of distributed key generation. We're going to look at the limitations. As with every technology, there are pros and cons. Now, when we look into the limitations, right, we should also look into what are the proposed solutions. And that's what we are going to do in the sixth section. The future development of DKG is exciting, whether it be in terms of blockchain technology or secure communication, multi party communication, and that is something that we will explore as well. On the seventh, there are some miscellaneous topics of DKG, including one where some researchers are trying to reduce the computational cost by applying sparse metric DKG algorithm. And at the end, we'll summarize the content uh, and the necessary references. And we'll also take a look at the offerings of bounties and hackathons by DoraHacks, where developers and hackers like me and other budding hackers and developers are learning about Web3 and are also getting rewarded for the same. So let's understand what distributed key generation means. So when the term stands for itself, like when we are generating a key through distributed parties. Now, this is not essentially basically generating a key and distributing it. No, this is distributed key generation. So basically, we are gathering parts of key, assembling it from different individuals or different entities, nodes, and then assembling a key. We'll go into like public key and private key uh, in the upcoming slides. But for now, it's just a technique through which we can generate a shared secret key. As I said, this is generated through collecting parts of these from multiple parties. It can be institutions, it can be nodes, it can be single individuals. Now, this ensures that not a single individual doesn't hold an entire key, right? So basically, we are not entrusting a key to a single individual. It's computationally generated by parts of keys through different individuals. The same now through this we can use it in blockchain technology because it's quite similar to decentralization. It's quite it uses the concept of decentralization to gain its motive, and thus secure messaging platforms can also use this. So, just a quick mention of history. It was first mentioned by Torben Peterson in 1991. The first concrete model was dependent on the joint Feldman protocol for verifiable secret sharing. How verifiable secret sharing works, I will give a glimpse in the upcoming slides. Then there is a collaborative process. This that we are having a threshold number of individuals, and then they are giving a set of a part of keys each to generate a whole key. Now, here is a pictorial representation or even illustrative example of how key splitting versus DKG works. So basically, when we are key splitting, we are generating a key and then we are distributing it among different operators. When we are working with distributed key generation, it's basically kind of like opposite. We are taking parts of these keys from different operators and generating a validator key. Now we saw that here basically you have a single key being generated somewhere. So this is again a centralization risk that traditional key splitting techniques come up with. The resiliency against attacks is better when you are going with the distributed key generation. And the implementation and practicality, as we move from the world of Web 2 to Web 3, DKG is better suited for it. It's better tailored for it. So this is a simple way how you can apply DKG protocols in your applications. Let's look at the core concepts. You have decentralization, as already mentioned, that the key is not through one centralized entity. It's not entrusted upon one centralized entity. So it saves the risk of single point of failure or corrupting a single individual. You have verifiable secret sharing, where you enable participants to receive partial secret keys and public keys. And then basically, if you have the secret key being divided among different nodes, that is something that you can't corrupt. You can share the public key, but if the secret private keys are shared among different nodes, it becomes difficult to corrupt or to manipulate. The robustness comes with DKG protocols because you have a strength of threshold. When we are talking about the threshold here, let's imagine you have an X number of individuals in a network, and the strength of the threshold is T. So basically, the T is less than X, and its T is the number of participants which you can corrupt without damaging the network. But once you cross that threshold, once you cross that T, that becomes effectively you're corrupting the network or manipulating the network. And so here, if you're keeping the threshold high, if you are using distributed key generation, then it basically becomes more secure. Now, let's talk about verifiable secret sharing. Here is a key image. I will go back one slide just to give you key points, right? But before we do that, just a pictorial representation of how the elliptic curve comes into play, secret generation. Observe that we are distributing the key among different individuals, and then we are using a threshold amount of individuals to generate a secret. Right? It's just a simple representation. It's scalable to many nodes. It's many individuals. And elliptic curve random functions is again a mathematical concept which is out of the scope of this workshop, but I would encourage listeners to explore and learn about elliptic curve random functions and how they can be used in conjunction with the distributed key generation, and thus it would create more secure systems. Now, we are again, when we are coming up to distributed key generation, we are generating a public-private key pair, right? While all parties learn the public key, no single party learns the secret key. No single party has the whole secret key with them. Parts of secret key goes to different individuals or nodes, and the public key is with all of them, right? And when we define a threshold, right, that these number of individuals, when they come together, they can reconstruct the secret key. So that enhances the security, that prevents us from single point of failure. Right? And also, when we're defining a strength of the network, we can say that, okay, fine, you can corrupt 5 individuals and the network won't go down. But you corrupt the 6th one, the network would go down. So 5 is the threshold, basically. Now, we will go forward with the practical aspects of the distributed key generation. We have formalized protocols. When you're talking about the Web3 world and as how the protocols for the world of Web3 are being designed, DKG plays a very crucial role. when we are talking about the upcoming messaging platforms, whether it be on Web3 or Web2, and especially on Web3, where we are trying to protect anonymity, we're trying to protect the security of the network, we're trying to decentralize the network. There, we can use the concept of threshold reconstruction. So it makes it resilient against attacks. We have fault tolerance and trustlessness. When you talk about trustlessness, you don't need to trust upon a single individual, like the way you trust upon banks to keep your money, or you trust upon Facebook or Instagram to take care of your data. We know how that played out. It's basically we are trusting upon the mechanism, not an individual. And the mechanism is basically the code that's running and the protocols that are being defined by the people, and they are basically operated by not by a single individual entity, but by the whole network. Now let's look at the applications of distributed key generation. Blockchain technology. I think this is something that is quite evident even when you talk about distributed key generation and decentralization blockchain technology. One thing that I would recommend the listeners of the workshop and everyone who are in the blockchain space to explore MPC wallets. So I have seen a lot of people using MetaMask, and basically even I use it to some extent. But I'm talking about the keeping the funds secure, like keeping a long-term fund secure, and making it more robust and resilient against attack. I would appreciate if people would explore MPC wallets like Zengo wallets, Sepura wallets. This is in no way in conjunction with them. It's just that I have explored the services, and they are pretty well against MetaMask or something like where they are again not using the MPC technology. The secure messaging platforms that are going to be generated in the future or are being used in the Web3 space by a niche amount of users right now, they would be or they are benefited by the distributed key generation. You have decentralized identity management. So kind of, let's say, if a concept, if we go and explore that you have an identity documents with you wherever you go. When you go to airport, when you go and use public transportation in any country. Let's say if we create a system where we have a singular identity management NFT, and for people who don't know, NFT are non-fungible tokens, basically something unique on blockchain. And if we are able to generate a decentralized identity through those NFTs, well, let's say if I want to reveal a certain part of it, like address proofs and identity proof to at a certain location, and I don't want to reveal more details about myself, then we can create dynamic NFTs around it. So this is just a simple application on the aspect of decentralized identity management, that we can establish assets not in terms of monetary value, but in terms of identity management and identity recognition, where decentralized concepts are used. Then we have signatures and authentication. So whether it be your resume or mark sheets or paying your rent, transportation, education, in any single way, if it's done on blockchain, it can be done in an instant. And it's also more reliable and secure rather than as compared to the traditional media. And when we apply the concept of distributed key generation, or just look at how it's working, you understand that it is way more advanced than the current traditional systems. And so this is something this is a matter of time. It's not if, it's when. Uh, and it's just a question of when. And we are going to see a lot of advances in the field of signatures and authentication, whether it be on the retail side or on the industrial side. Now, as in with any technology, we are looking at some limitations. at DKG. Now it has very few limitations, and especially I think it's way better than the current technology, but it's still something that we are. It's something like some gas fees being observed on certain blockchains, and then better blockchain scheme. So it's kind of an improvement will happen in the upcoming years. So you have complexity and overhead, which is a key limitation of distributed key generation. When you have multiple parties participating in the key generation, it can potentially impact the system performance rather than one individual taking care of everything. Now, that basically is a question of trust versus complexity and the trade off that you are going to make. Trust assumptions. Now, in the previous slide, I mentioned trustlessness. So I'm just going to say that trust assumptions, when you're talking about trust assumptions, we are talking about the generating parties, generating nodes involved. We're not talking about the mechanism in between the generating parties and the final key generated. So when you're talking about the mechanism in between, that is trustlessness, that we don't have to trust any individual. The trust assumptions that we are going putting to achieve this trustlessness is that the individuals at the end who are generating part of keys, right, that we are assuming are not malicious, and that they are securely generating and managing those parts of keys. Again, if one individual is not managing and generating it or managing the keys properly, then it's okay. But if a threshold is reached, then malicious actor can activate his intents. Communication overhead is already explained, and then there are security concerns. Again, way lower than the traditional systems, but there are still security concerns with potential collusion among participants, compromised nodes. Now, let's look at the solutions in future of the distributed key generation. We are going to have to design more efficient protocols that basically eliminates the communication overhead and computational complexity. Trustless models, even at the point of generation of those parts of keys, with the enhanced security mechanisms like zero knowledge proofs. So zero knowledge proofs is again a very interesting concept when we talk about blockchain technology and how things are going to go in terms of sign-in authentication on Web3 especially. To explain the zero knowledge proof, I would give a basic analogy. So let's say you have a colorblind friend, right? And you are holding two balls, a green ball and a red ball, each in one hand, and you have to prove it to your friend, right? That you are in one hand you are holding a green ball, in one hand you're holding a red ball. Basically, the two balls are of different color, and you know that the friend is colorblind. So how are you going to prove this to him? Right? So what you can do is give the balls to him, in his hands, and then ask him to switch it, right? Switch the balls from one hand to the other hand. Like, so if he is holding the red ball in the right hand and the green ball in the left hand, he can switch it, and he should switch it in a way that you can't see, right? So you can put his hands on the back, switch the balls, and then ask you that whether I have switched the balls or not. So now you exactly don't know, right? He can have put the red ball in the same hand, green ball in the same hand, and could have presented to you again, or he could have actually switched the balls, right? But you would know after you see the colors, right? Because you initially saw that red ball was in this hand, the green ball was in the other hand. Now they have changed places. So that's how you can say that, yeah, okay, the balls are in different hands. Right? So that's how you can prove to him that the two color balls, they are of different colors. Because if they were not of different colors, you won't be able to identify. Right? Now, one thing that you might say is that it can be a matter of luck. Right? First time you guessed and you reached the right conclusion. So you can repeat those experiments, and if you are able to guess 10 out of 10 times, which you would, because you would basically see that before the state change, the red ball is in one hand and the green ball is in different hand, and after the state change the situation is different. So you would be able to know, and after you repeatedly tell him that no, the colors are different, now you have made the switch. So the only way you would be able to identify is that if the colors are different. Okay. Next, we have trustless models, and again, I told that if we are able to generate trustless models in a way, at the point of generation of parts of key, there are no trust assumptions, then we would be in a much better state of distributed key generation. And then there is scalability solutions. So if we are able to keep the efficiency, security, and performance while scaling these solutions, and there are some practical challenges that research teams are facing, but if we are able to scale this, then it would be an exactly a practical way of communicating and technology evolution. Just a matter of when, not if. Now, some miscellaneous topics of distributed key generation. Efficiency in computation. So here it's a simple graph where high performance cluster, single computer, and we are able to see that with the problem size, how the computational efficiency is growing. Okay. So performance of DKG on different computers and how we can basically improve the efficiency, that's something that we need to focus on. A sparse evaluation metrics. So for people who are well versed with mathematical concepts and people who would like to read research papers, I have attached in the references. I'm going to show one research paper. Basically, it's by people at University of California, Berkeley, where they have reduced the computational complexity from big O and T to a more optimized level. Basically, they have reduced it to log cube n, which enhances the verification process and overall system performance, which is something, a system performance is something that was a key limitation, and we are solving it through such measures. Applications in key escrow services. Now, that is something that's pretty evident that when you have funds being stored in a single place and communication between the client and the person who is delivering the services, this can be pretty useful. Group digital signatures. So let's say you are managing an organization, and now we are assuming that the organization has moved to blockchain. And for the approval of a new idea, you have a group of individuals. Now, when you're talking about these blockchains, we're talking about blockchain technology like Hyperledger. Basically, that can be used in organizations where some individual have more rights than other individuals. It's in the blockchain technology, means we are keeping it on chain, and we are defining this by the organization that the CEO would have more signing rights than the employees in a simple way. And so if you have a group of stakeholders who want to pass a decision, there we can use this group digital signatures, that once they come up onto whether they want to hire this individual, approve this idea, how they want to go in this next quarter, then that is the concept that we can explore. So now we are moving to the conclusion. So distributed key generation, as stated, it offers a secure and decentralized approach, enabling multiple parties to collaborate to generate cryptographic keys without central authority. Just to summarize the concepts, DKG protocols or distributed key generation ensure security. Even when the compromise of malicious participants are there, we just need to make sure that the threshold is not crossed. Decentralized trust, we discuss the efficiency in applications and also the future innovations that are coming into this concept. Now, as I was talking about the research paper, interesting research paper, I think, yeah. Okay, just a minute. Okay, there are some issues with the research paper. I would open it shortly after we go through the last section. The last is Nikki K's Game of Trust. So basically, this is an interesting game of trust that individuals can play to understand more about game theory and how communication mismanagement can lead to a disaster. So it's just a simple. I would show the simple first step. People can individually play more with the game to understand the concept of game theory. This is, during World War One, peace broke out. Christmas 1918 on the Western Front. Strict orders not to relax. British and German soldiers left the trenches and crossed the no man's land, gathered to bury their dead, exchange gifts, and play games. Now, this game is a little bit old. It was 2017 when it was released, right? Right now, it's a different situation, but yeah, I mean, we are pretty much at peace as compared to what it was in the First World War. So, so this is a game of trust. Uh, if people have played this game before or are aware about what this is, this is for the people who are not aware. Just a basic introduction. So the other player puts 3 coins. If you put a coin in the machine, the other player gets 3 coins and vice versa. So basically, what happens is that let's say if I cheat, the other player cheats. If I cheat, right, we both don't get anything, right? If they cheat and I don't, I reduce. I get my points get reduced by 1. They get +3. If I cooperate and they cooperate, right, we both get equal points. And if I cheat and they don't cheat, I get +3. So if even if the other player is cooperating, if I want to maximize my advantage, I would cheat. We can basically, yeah. Now that's a little bit mean, but that's also the optimized answer. We are allowing ourselves to maximize the advantage. Right? Let's see what happens when you do this more than once. Okay. The first time we want to cheat because even if he cheats, right, and if we don't, then he would get +3 and -1. Just on the safe side, we are going to cheat. Okay, they cooperated, right? So 3 -1. Now let's understand what if we cooperate. So now they cheated. Right? So basically, let's just cheat again. Okay. So now we are getting 5-1. Okay. Now, what if we cooperate, right? Again. So then we got 4. And now, let's say we cheat again. Now it's 7. Right? Now the player has changed. But you can see that if we had cooperated, because the player was intending to cooperate with us only if we cooperated. And if we cheated, they are going to cheat as well, right? For the once. And then the next chance, there is different talk about how he's going to respond. But if we cooperated, we would have 10. And I think both the players would have 10 in that scenario. So we have different players and different things about trust and trustlessness. We talked about trustlessness and trust in the past and how it's established. This is more about the game theory and the game of trust. So you can explore additional steps. There are more nuances to this, more kinds of individuals, because not everybody is going to cheat, and there are individuals who are going to cheat with you irrespective of what you do. So, there are some individuals who are going to cooperate irrespective of what you do. So, how are you dealing with different individuals? How you are playing the game of trust? I think that's what's discussed. So, yeah, I think you can explore that. Now, talking about the last Berkeley paper, I would just go ahead and share that. You can copy it on the screen. It's there, but I would try and open that again. No, it's, yep. Yeah, so this is a practical large-scale distributed key generation. Paper written by John Canny and Stephen Sorkin. So they have presented a randomized algorithm called sparse matrix DKG and reduced this cost, which was basically omega nt to omega log cube n. Right? We are assuming that this is the presence of sigma and malicious parties. Okay. So this is something that you can explore. The links to the required references for preparation of this workshop and such more unique articles are given. We already went through the Nikki Case Game of Trust. You can search this URL or just write Nikki Case Game of Trust on Google and you would get there. So yeah, I would like to thank DoraHacks and Dōjo. Basically, you can go to the website of DoraHacks. They are providing with amazing bounties. There are amazing large pool hackathons are coming. There is Cilicia, there is Data Economy Hackathon, Akashathon. I'm looking to dedicate more time towards participation in these hackathons and bounties. So people who are budding hackers and developers should look into this. And yeah, I think you can contact me on email, connect with me on LinkedIn and Twitter. And yeah, that's pretty much it. Hello?
Hi guys, thank you for your presentations and we can end now.
Yeah.
Okay, see you next time. Goodbye.
Goodbye. Yeah.